Yeah.
CBS roll.
Oh,
So excited.
it's nice.
You be the next question.
I think so.
No, it's never gonna get old that long.
Yeah, I guess we'll start with small class. All right. I mean, up to this point, we covered data storage for single bit data storage, latches, flip flops, that sort of thing. We're going to cover more extensive storage techniques with multiple bits, words, that sort of thing, and methods of moving the stuff around. There's a couple of characteristics they classify it as. One is capacity, which is the number of bits that a digital gate can store, or a combination of digital gates. And the other thing is capability. What can it do? We heard the term, I guess some of you guys have heard the term shift registers, shift left, shift right, rotate, all that other jazz. There's, combinations of gates to do that. They're generally included in a family of serial data transmission, back and forth. UARTs, universal asynchronous receiver transmitters, that sort of thing. That was back in the day. I don't even know if they use them anymore. But they're more or less for handling serial transmission, so you limit the amount of lines you need in a bus structure. So instead of, if you're moving 8 bits around, instead of having 8 conductors, you can serially move the bits through memory through a single conductor. It takes a little bit more time to do that, many more clock cycles, but yeah, exactly. So it's somebody trying to come in. So we talk about the basic latch. Latch, R, and we got enable. And that's obviously for a single bit. So if this is a 1 and enable is a 1, we set the Q bit. So we're storing a 1 in it. That's the typical latch. And then the JK edge triggered device is considered a flip flop because it moves in sequence with the clock. It responds with the clock. And specifically the edges, the rising and falling edges.
S is set, R is reset?
Yeah, set and reset. Yep. So if we set the bit for 1 and we have an enable 1 here, we're going to have a 1 on the Q, the response.
That's an
Yeah, this is a NAND operator. Yeah, it's a NAND gate system. Yeah, and we start to move away from that stuff, like the individual gates. We just did it for analysis, as far as signals. Most of this stuff though is in a block form like this, and it's written in a simplified manner so you could follow data flow. With the JK flip-flop, this is a latch, and this is the flip-flop. And the only difference between a flip-flop and the latch is the clock, is the rising and falling edge of the clock. And I'm going to show you guys that on the oscilloscope with this system generator that I have, the microprocessor system. Everything is coordinated with the micro's clock output. So if we have a clock pulse like this, and we're looking specifically at the rising edge, there's no bubble here. So if we say, in this instance, we say 1 here for K. For Q, we're going to have a 0 output because we reset the flip-flop.
So I'm trying to put what you're explaining into like practical terms, right? So that latch would be pretty much that's one state that latch could be in.
Exactly.
So that would represent, let's say, whatever on a screen or however it's applied.
Right.
And then you can reset it, and then it now takes a different.
Exactly. Well, this latch is going to interface with, you might see something like this interfacing with a sensor or a switch.
Yeah.
A switch is a long-term, it's temporary, but it's a long-term operation. You throw the switch, it stays there for a while. You just want to store what was out there.
Okay.
You know, that
So
condition.
That's pretty much what kind of memory is. It's just a latch state.
Right, right.
Am I
It's a latch, it's a memory
It's a
state.
memory
It's
state.
one memory state, yeah.
Okay.
So this is monitoring one switch or one sensor,
Yeah.
you know. This is monitoring something maybe a little bit quicker, you know, where you need to look at the rising and falling edges of the clock. Something, there might be a quick event, and you have to look at that event. It might be a sensor or let's say a thermocouple, temperature reading, or it might be something coming in from a CAD cell, something like that, where we have to sample it really quickly. A switch it has some latency to it. It takes, you know, it sits there for a while. So a level enabled signal is okay. You know, for the amount of time that the clock is high, then we can store that bit. We're not worried about time.
This is what you were using as an example for contact bounce the other day, right?
Exactly, and that's
For the latch.
And that was the other purpose, is contact bounces, because the latch acts like a one-shot circuit. In other words, if you had a very quick transition like that, and we want to know if, let's say, we want to detect some kind of a glitch out there, the latch would detect that glitch and stay high. Or if we're using it for contact, you know, for contact bounce elimination, where the switch kind of bounces back and forth before it finally settles, on the first strike, it remains high. So it's ignoring the noise, you know, because that'll foul up the sequential operation of the system. You know, so those are the primary reasons for latches and individual flip-flops like this. Now, what Damien's going to go through in a little while is the combination of flip-flops using frequency divisions and that sort of thing, and can actually follow it through with the clock signals. You know, but these are the basic components of a microprocessor system.
Those two components are made.
Yeah. These are more or less input components. They clean up the signal. They store temporary information. The microprocessor wants to run at a very quick rate. It wants to pull that data and then just do some processing. So you want to capture the first sequence of changes on some kind of an input device. And that's what the latch does. It holds the data there for a period of time. You know, it's like you can consider it like a sample and hold type arrangement, which we'll be talking about later on down the road for sampling. But one's edge triggered. This is called level enabled, where we don't care about the clock. It's just this period. Anytime the clock is high, it's sensitive to what's on S. If S decides to drop, it's going to reflect, and we don't want that. If you're looking at it for something that happens very quickly, you want an edge trigger device like that.
Okay, now you've got, continue with the flip-flop.
Yeah, that's the flip flop. That's the primary difference between the two.
Okay, now that, as long as K stays 1,
Yep.
when the next time you have a positive going edge,
Yep.
which would be the beginning of the next cycle, then you would flop, the Q would now become 1.
Right. So this is going to stay 0. So if we were high, it's just going to stay 0. It was triggered, and that was it until the next clock cycle. Then it looks at the next pulse. You know? But this might be, the microprocessor might be only looking at it for a very short period of time. You know, or it might sit there and say, I want to hold that last value. You know, so it has something to reference. It goes back to the Q, and it references what was on the Q. You know, for some kind of an operation, mathematical, logical operation, which we'll talk a little more in detail when we do the microprocessor. But like I said, these are the basic elements of storage. You know, like I said, it's frequency division is one aspect of it, which Damien's going to go into, which they call them the JK flip-flops for toggle operation. Sometimes they call them toggle flip-flops, and they're just combinations of Ds and JKs, that sort of thing. A D flip-flop is nothing more than a JK with an inverter. And the JK is basically the primary system element. So with that, I'll let Damien.
You want to go through the JK?
You know, maybe just maybe just one other thing real quick. This is on the test too, I just want to mention. When you have a data bus, right? And let's say this is the data bus here, this is D0, and this is D0 out here. This might be input, and this is output. What happens is, they might do something like a read operation. They want to read something in from an I/O device, which could be a sensor, or something on the output. Or they might decide the micro wants to go in the other direction, wants to write something out to memory. So you don't want data going in two directions at the same time, because it causes bus contention. They contend for the same bus. So the micro has a control line, and it feeds a set of buffers. And one buffer is enabled low, and the other one is enabled high. So depending on this control signal, it's either 1 or 1 not, like that. It can steer it, and this might be, for the not, this might be a read operation, and this is write. So the micro basically raises or lowers that line, saying, I'm either going to send something out to memory, or I'm going to read something in from some switch out there.
So see the same, okay, I'm taking in input, putting on an output,
Right.
pretty much, according to another control micro, I guess.
Right, because this peripheral device is just sitting here, and it has the data available. It's there. The data is there all the time. The micro doesn't want to be sending something out to another device, and this thing is contending for that same bus. So it shuts that bus down with these called tri-state buffers.
What is going to happen on the same bus?
Yeah, they share the same bus, but they put these little devices on it. They're 3-terminal devices, and they basically shift the bus one direction or the other depending on where the micro wants to be.
Are those the right symbols for that?
Yeah, yeah. This is a buffer. It's like the op-amp type symbol with a single input.
Okay,
Yeah.
the one on top of that coming in from the not signal.
Yeah, I
coming
drew
in from the
like a
top.
right angle, but it's not really a right angle.
So that's the definition of a buffer.
Yeah, that's a buffer. This is, it's more like this.
Okay.
Sorry. So basically, like I said, you have data moving in one direction or it's moving in the other. If I enable this high, this buffer is like a switch inside.
Transfer switch.
Yeah, the switch is closed. So it's allowing data flow this way. This switch is open. This is a high impedance state. This is high Z. So what happens is this guy is open, this guy's closed, so we have data flow this way. Then if we flip it, if we go low, this guy's closed, this guy's open, so data flows the other way. So they call it bus transceivers or tri-state communications, that sort of thing. You know, and I'm not sure how they represent it on the test, but they have this particular question, right, Damien?
Yeah.
And they ask that reason. They actually show the symbols, and they show what happens if it's low. Which direction is the data going?
And that's all they would have to answer?
That's it, yeah. So I figured we needed to cover it. But they're called tri-state, this is a tri-state buffer, this individual device, and then this is called a bus transceiver. It transmits and it receives. It's a transceiver. But it's like one question on the test. So it's D0, D1, D2, D2, every bus has it. The other thing is they do, like in the microprocessor system that I have here, is they share the bus with the address and data lines, which we'll talk about later too. Where in one direction the micro's addressing a particular device, and the other direction it's actually reading data back from the device. So it's actually sharing the same lines. They call them address data, /data. So it's ways of simplifying the routing of printed wire and traces and what else. So otherwise you'll have a billion traces on it. All right?
Yeah, want to do the all right. Has that this one. So John mentioned the JK flip-flop. The JK flip-flop internally they tie high. This is J. That's K. And this is a 1 right here.
Are those programmable or it's always going to be high?
They're wired high.
They're wired, they
Yeah.
always have
They
one
always
coming in
are
there.
high?
Yeah, yeah. So in other words, it's a fixed input. They're not.
Okay.
They're not worried about it.
That's the clock coming in here. That's Q. And that's we get a clock. And we just call this stage 1. Alright. Now when you see this little symbol right here without a bubble, it means it's looking at the clock on the rising edge. Alright? With the bubble, if it had a little bubble right here, it's looking at the falling edge. So in this case, what I'm going to explain is with it on the rising edge. So you have your clock coming in. All right, your clock coming in. This thing won't detect an output until every rising edge. All right, so we're going up. So we go up. That's the rising edge. Go down, go up. That's the rising edge again. Go down, rise. So at that frequency, when you come in on your output, you're gonna have something like this. It detects, it's on the rising edge, it's gonna go across, it detects again on the rising edge, go across, it detects on the rising edge, go across, it detects again, and it goes out. You see what happened? Anybody kind of see what happened right there? Look at this versus this. What a difference.
Division by 2.
It's divided by 2. So divide the frequency of this clock by 2. So that's what the JK does. It divides the frequency. So let's illustrate a little more. Let me say if we put one more JK. So we put one more JK in. Alright, we come in right here, we got J, got K. Here, let's do that. Alright. And so this is going in right here. So the clock going in, these things are tied together. Again with the 1, just the same way. What you kind of expect to come on the output here? We call it output. What do you think is going to happen now? Because this is now feeding this one.
You're going to continue division with the stage 1 being your clock.
Right, so you know your stage 1 is your clock. So now this goes up on the rising edge. Goes down. This is your rising edge. Go down, this is your rising edge. So now your stage 2 is saying, okay, let's go up. We go across, we're going to do nothing until we go down. We're going to do nothing again until it goes up and continue. So now this, divide by 2 also. You keep adding them like that, you keep going and going and going and going, so you got a long frequency, keep dividing by 2. That's pretty much what a JK flip-flop does.
And that's only possible with an edge-triggered device. If you have a level enabled, like the latch, it doesn't do anything. Toggle means it's going to flip. It's going to change state. Every time it hits the clock, the rising, it's going to change state, back and forth. Yeah.
Well. I mean, that's pretty much it for, there's really nothing, much to it. Every different, one of these flips up there.
What is that? Practically, would you use that type of, how's that used?
Well, in this microprocessor system here, I put a chip in there that only runs, it's at a maximum clock frequency of 4 megahertz. But I had a crystal of 12 megahertz. So what I did is I divided down 3 times, to get that operating frequency for that microprocessor.
Well, the crystal meaning where you got your clock frequency.
Exactly.
That's where your frequency comes from.
That's the frequency that the micro's going to run at. So I basically divided down the frequency with JK flip flops.
Yeah, it's kind of like, say, you got a supply 12 volts then or something like that, and you got a chip that needs 6 volts. You kind of, just to equate voltage to it. You would use something like this just to step it down. Like